So hello everyone. Today we're going to have our second class on information retrieval. It's related to the last lab that we saw, and we're going to talk specifically about ranking, so the order in which we'll see the results. So, in terms of the overall structure of the course, we're still in this topic of distributed unstructured data management. So how to index and deal with lots of text using lots of machines. So in terms of what we saw in the lab, we used an inverted index called Elasticsearch, which is built on top of Apache Lucene. So we saw when we were doing the searches, I don't know how many people have done lab 7, hopefully a few of you, but you saw when you were doing searches that the results were not maybe as you expected. And we're going to discuss why that is. So maybe you search for Obama and you didn't get Barack Obama, or maybe you search for Trump and you didn't get Donald Trump, you got something else. So we're going to discuss a little bit some possible reasons why that might be the case. Okay. Okay, if you search for Obama, you would expect Barack Obama to come up, but it doesn't. Okay. So in terms of ranking, when we talk about information retrieval and the search of documents of text, for example, on the web, we might think of Google, right? And the question is, how does Google get such good results? So we take for granted almost that when we search Google, we've also gotten very good at using Google. So we could take for granted that we get such good results. So for example, if we search for Obama, we get some expected results relating to Barack Obama, for example. And that it can choose from millions upon millions of documents that contain this keyword term, which documents are the more likely to be relevant to a typical user. So these results look pretty good, what we might expect. So how does Google get such good results? Aside from simple keyword searches, I can do more. Google is good even for more complex queries. The search is that one movie where the guy breaks his leg and spies on his neighbor. If we search for this in Google, we'll get any ideas? Rear window. I think it's ventana oscura or something like that in Spanish. Da 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 dum symphony. Da 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 dum. Beethoven, see? Quinta. So Beethoven's Fifth Symphony. You can try it in Google. You'll get the search results. And Google also knows sometimes what we're even looking for. It can suggest what we're going to be looking for. Okay. So Google gets some pretty good results. And the question is, how does it manage this? So in terms of how Google gets such good results, Google takes into account many aspects. And we'll talk a little bit later about all the different aspects that Google potentially takes into consideration. But the two main aspects of ranking for most applications that we need to consider relevance and importance. Okay. So relevance means essentially that we get some documents that are somehow related to our keyword search. Yeah, they contain the term Obama. Maybe they contain it many times, for example. Yeah. So we somehow are looking for relevant documents for our search. The second aspect is that we want important documents. And what do I mean by important? Well, it's a broad, vague concept, but we'll see specific ways of implementing algorithms to measure importance. But essentially, we're hoping for, if we search for Obama, that we would be able to detect that Barack Obama is a more important result or more likely to be of relevance to a typical user than Mount Obama, which was named after him, for example. Okay, so we have these two aspects we need to consider, and we're going to talk about these. So, of course, relevance versus importance is a balancing act, and we need to somehow weigh up all these different factors and find a good balance for these. Okay, so we could have very important documents that are not so relevant, and we could have very important, very relevant documents that are not so important, and we need to figure out how to rank between these two elements. So the first aspect we're going to look at is relevance, and we're going to take an example to illustrate a very common way in which relevance can be measured. So we're going to take this query of movie Freedom Wallace. Any ideas what movie we're talking about? So this is Braveheart or Corazón Valiente. Yeah. So Braveheart. Okay, so we do the search, we get these results. So the question is, which of these three keyword terms is most important, most influential, would you say, of movie, Freedom, and Wallace? intuitively, which Wallace? Yeah. Why Wallace?
It's more specific.
Yeah, it's more specific, right? So movie and freedom are somehow not very specific, right? So Wallace is somehow more influential, let's say, in terms of relevance. So let's turn that intuition into an algorithm. Let's just take, for example, this result, which is the Wikipedia result for Braveheart. Let's have a look inside that Wikipedia article, and we can search inside this Wikipedia article, and we can look for the term freedom. Okay, so we see the freedom here, we search for it, and we see that there are 7 hits for freedom. Okay, so we have 7 occurrences of freedom in this document. We have 16 occurrences of movie, and we have 88 occurrences of Wallace. Yeah. So one good thing is, first of all 3 of our search terms appear in this document. So that's a good sign. We also have a lot of occurrences of the most specific word Wallace. So that also gives us some indication that this is a relevant document. Yeah. So we have 88 occurrences of the term Wallace. So if we search for Wallace, we get 88 hits, and we can see all the hits here on the bar. Okay. So in terms of the usefulness of words, if we look for a movie, we see that in Google, there are about 835 million search results. This is approximate number that Google gives us. So it's a very frequent, very common word, let's say. So it occurs very frequently in documents. Freedom, less frequent. So we see about 200 million results. So we'll say that this is a medium frequency term. And then we have Wallace, which has 49 million results. So we see that Wallace is much more specific than the other 2 search results. Okay. So we see that Wallace somehow intuitively is more specific. It gives us more information with respect to relevance than the other 2 terms. And it appears very frequently in this document we saw. And that means that that document should probably be highly ranked in terms of relevance. Yeah. So in terms of estimating relevance, we have this idea that rare words are more important than common words. So Wallace more important than freedom, more important than movie. And words occurring more frequently in a document indicate higher relevance. So since we have more matches for Wallace, that's an important word that gives us higher relevance than with respect to movie or freedom. So to turn these intuitions into an algorithm, this is more like a family of measures. These are ways of measuring the relevance of documents. There's this notion of TF-IDF. Have you seen TF-IDF in another course? No? Okay, so this is the base of many relevance measures, including what Elasticsearch was using in Lab 7 to do the scoring. Yeah. So it's based on these 2 concepts that we just saw, but measures for the 2 intuitions we just saw. We have term frequency, which measures the occurrence of a term in a document, tells us how many times a word appears. And there are various options for how to encode this. So the first is we can just take a term, for example, Wallace, take a document, for example, Wikipedia page, and just say it's the count of how many times Wallace appears in that particular document. Yeah. So we can have the raw count of occurrences, which would just be counting how many times it appears. But often we're going to normalize the TF. So often we don't want a huge number of appearances to count linearly. So we can apply, for example, a log function to bring down the extreme numbers or the documents that have a very high number of occurrences of a word. So we take the log of the count D plus 1. So we add the plus 1, so we don't take a log of 0. Yeah. We can also normalize by document length. So in this case, we can say what percentage of the terms in that document are actually of the term we're looking for. Yeah. So if we find 88 occurrences of Wallace in a relatively short document, we could say, okay, it mentions Wallace a lot, but if it's a huge document, maybe an entire encyclopedia or something in one web page, then that would not be so interesting. So we could also consider normalizing by document length. So again, TF-IDF is this family of measures, term frequency. We can instantiate that in some different ways. We're normalizing by the total word count in the document. Here, we're normalizing by the word that occurs most frequently in that document. Yeah, so both based on the idea of normalizing by document length. Okay, and we can have some combination or some other measure for term frequency. The second part of TF-IDF is the idea of inverse document frequency, where we're asking how common a term is across all documents. Yeah. So this is the idea of Wallace is a more specific term, so it should be more important. So in terms of IDF, we take T, which is the term, and we take D, which is the set of all documents, not a specific document, right? So IDF is not specific to a document. So we can count the logarithmically scaled document occurrences. This is the most typical way to measure IDF, where essentially we take the number of documents in total divided by the number of documents that contain that term. And we just add these ones here so we avoid dividing by 0 or taking the log of a 0, which we don't want. Yeah. So essentially, we take the number of documents and then we divide it by the number of documents that that have that. So the IDF before we take the log would say, for example, 1 in IDF number of documents contains these terms. 1 in 5, for example, contains this term. So the more rare, the larger the value. Yeah. So for this reason, we call it the inverse document frequency. Yeah? So it's like the inverse of the percentage or the ratio. So TF-IDF, what we do is combine term frequency and inverse document frequency together into one measure. How do we do that? We just typically multiply the term frequency by the inverse document frequency. Yeah. So we expect when we say multiply, it's sort of like an and. We expect both values to be high to have a high score. If one is very low, then that will tank the score. So it will create a very low TF-IDF score. So TF-IDF, we multiply. This means we're expecting both TF and IDF to be high to have a high relevance influence. So the score for a query then, this is just for one term. If we have a query that has multiple terms in it, the score for a query will essentially be the sum of the TF-IDF scores. Yeah, for each term. There are other possibilities. So just to briefly mention some refinements on this idea, sometimes people will implement in their measures some sort of factor of how many terms appear. So maybe if all 3 terms appear from movie Freedom Wallace, it gets a bonus. If only two appear, it gets a penalty. Also, there can be other possibilities. We'll see one of those later, which is using the vector space model and cosine similarity. So, okay. So to take an example and work through an example for our movie Freedom Wallace query on the Wikipedia page for Braveheart, we have our measure for term frequency. We're going to instantiate that just with the raw count of how many times the word appears. And we have our inverse document frequency, which we saw is the log of the inverse of the ratio of the number of documents that contain the term. So let's calculate specifically this to illustrate how it goes. So we have our terms movie Freedom Wallace. We have how many times each term appears in the document in this case being the Braveheart example we saw. So 16, 7, and 43. Next, we have the number of documents that contain the terms. So we saw that in Google, we had 835 million hits approximately for movie. So we'll take that as the count of documents with movie. Here we have the count for Freedom, and here we have the count for Wallace. Next, we need to calculate the inverse frequency. Okay, we add some ones here to avoid the 0 case. For this, we need one more data point that we have not seen, which is how many documents are there in total. So just for the purposes of example, I'm going to take Google search results for which gives me about 11 billion results. So I'm going to take that just for the example as the number of total documents. So then we're going to have 11 billion over 835 million, 11 billion over 198 million, and 11 billion over 49 million. And we get these results here. So this roughly tells us that 1 in every 231 documents contains the word Wallace. Yeah, this is what the IDF tells us. We take the log of this. That gives us the inverse document frequency instantiated here with the log of 2, could be log of 10, whatever we might want to use. But here we get our IDF score based on a log of 2 of this value here. And finally, we multiply the TF and the IDF and we get our final score here, which is the contribution to the relevance of each term. So movie is giving us a boost of 60, Freedom of 40, and we see that Wallace turns out to be much more important, 337. We take the sum of those and we get our final score for the relevance of this document for this query based on TF-IDF, 439. 439 what? There is no units. So what we care about here, since we're ranking, is the relative order that this induces on the scores. Yeah, so we don't really care about the units. We just want to know which documents have a bigger or smaller score, and then to show those first to the user. Any questions on this part? All good. Okay, so TF-IDF is a very widely used measure for information retrieval, also maybe for aspects of natural language processing. There is another way. So I mentioned that we can, for example, add to compute the score for a query with multiple terms. We can sum up the TF-IDF scores for individual terms to get a final score. We can also use something called a vector space model. Maybe you've seen the vector space model before in some course. Yeah, in this case, yeah. Okay. So we'll go through it quickly and mention a couple of details of what the vector space model does. So in the vector space model, we have some sorts of dimensions. In this case, the dimensions, we have a multi-dimensional space. In this case, we assume that each dimension is a term of our query or of the documents or whatever it might be. So we have a dimension for Wallace, freedom, and movie. So given a document that contains movie 16 times, freedom 7 times, and Wallace 43 times, this creates a vector in the space. Yeah. So the first thing we're going to do with this vector is we're going to normalize it to create a unit vector. So this is the length or the magnitude of the vector. Yeah, so we take the sum of the square of the components of the vector. We take the root of the sum of the squares of the components of the vector. That gives us the length of the vector, as we see here. We see the length we see here the components squared, and then we take the sum of them and we compute the length. Yeah. So what we're going to do is we're going to normalize the vector by the length to create a unit vector in the space. So a vector of length 1. Then we're going to consider this vector in the space where we go 0.34 in the movie direction, roughly speaking, 0.15 in the freedom dimension. And then we're going to go up 0.92 in the Wallace direction. And that gives us our vector or unit vector representing this document. Yeah, in this vector space for this query. So we see here our vector. So this is of length 1, this vector, because we've normalized by the magnitude of the vector. So divided by L normalizes the length of the vector to 1. Yeah, so if we consider a different document, which we won't go through the numbers exactly, but let's assume that there's this other document D prime. It has a vector 0.49, 0.182, 0.3. So we see that we have a second vector in this vector space representing another document with respect to the dimensions of these terms. So over these two vectors, if we want to see how similar they are, we can use cosine similarity. So we could compare two documents, we could compare two searches, we could compare a search with a document, whatever we might want to do. So how we can compute cosine similarity, effectively, we can take the dot product of both vectors, and that will give us a notion of the similarity of these vectors. Yeah. So what is the dot product? Essentially, what we're going to do is for each component of the vector, we're going to multiply them, and then we're going to calculate the sum. Okay. So we multiply all of the components, and then we get some sum for the similarity. Okay. So this is called cosine similarity because the dot product of two vectors is equal to the multiplying the magnitude of the dot product of vectors A and B is equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between A and B. And in this case, since A is a unit vector, this is 1. Since B is a unit vector, this is 1. So if we take the dot product of two unit vectors, it gives us the cosine of the angle between those two unit vectors. So for this reason, it's called a cosine similarity. So since this is equal to 1, what we're essentially computing is the angle between the two vectors. And we assume that if the angle is very small, then we want the similarity to be very high. Yeah. So the smaller the angle, the larger, the greater the similarity. So hence the similarity is the cosine of the angle between the vectors. So when I mentioned before that there's other ways to score a query, a really common way to do this and also used by Lucene and by Elasticsearch is to use the vector space model. to compute this. Yeah, so we could use the cosine similarity between the query and the document using TF-IDF weights. Just to mention, sorry, briefly here, that here I just used the TF weights, but we could also use TF-IDF weights. So if I go back here, if we looked at what the components of the vector were, they were just TF weights, but we could also apply TF-IDF weights to compute this. Okay. So you've seen some of you have seen the vector space model before. So we can combine the vector space model with relevance measures like TF-IDF to score documents according to different queries. So this is essentially what Elasticsearch is using. There are a couple of other details in terms of finding, documents that are relevant that contain the actual keywords that we're searching for. So one aspect that you saw as well in Lab 7 is the notion of field-based boosting. So there was this weird boost variable that had a value of 5 for title and a value of 1 for abstract. What this was saying is that if a word appeared in the title, it was 5 times more important than if it appeared in the abstract. So intuitively, if we're searching for a document and somehow our keyword searches are in the title rather than in the third paragraph of the document, that indicates more relevance. So we can use field-based boosting in order to deal with this. So we can say, for example, that hits in title, for example, the fact that Obama appears in the title here is somehow more interesting than if it appeared in the 5th paragraph. Okay, so field-based boosting is very commonly used. It's something we can also do in Elasticsearch. Another important aspect is the use of anchor text. So we not only need to, we can not only index the content of a document, but we can also index the text used to link to that document from other documents. So what does this mean? It means that here, for example, we have some web page and we have a link to the Braveheart Wikipedia page, some completely remote page. And in the link, the text for the link, the anchor text, states a movie about William Wallace called Braveheart. So we can take this text as a description, open description on the web of what this page is about. And we can also say, maybe take some of the context of the text surrounding that link. So set in Scotland, it has lots of blood and gore. So this is probably also how, for example, da-da-da-dum, how Google knows that it's Beethoven's Symphony No. 5, 5th Symphony. Even if the web page doesn't mention da-da-da-dum, if people link to that web page and use da-da-da-dum a lot, then it can pick up that somehow this page is very relevant for this search. So we use not just the content of the document, but we can also use the links to that document and the text that describes those links as content for search. Yeah, so this is probably how, for example, da-da-da-dum occurs, although maybe in the comments as well of the YouTube video, the text appears as well. So Lucene uses relevance scoring, and in turn, Elasticsearch uses Lucene. Effectively, Elasticsearch delegates all of the indexing, search, relevance ranking, all of this to this underlying Lucene library written in Java. Okay, so this explains more or less what you saw in Lab 7 and what the ranking results were giving you. They weren't maybe always the results that you would expect. Any questions or doubts about that? No. Okay, so we have a second aspect of ranking, and this is the notion of importance. So what do I mean by importance? I mean that somehow some results are a priori more likely to be of relevance to a user, because they describe a more important entity or an entity that's more well-known, or it's a well-known page. For example, many users would like to see Wikipedia results early in the search results and so forth. So importance, this idea in this case that if we search for Obama, we expect maybe someone like Barack Obama, who's sort of more well-known than maybe some hill called Mount Obama. That's relatively obscure. So how could we determine that Barack Obama is more important than Mount Obama as a search result for Obama on the web? I'm saying Obama a lot. Obama. Any idea how we could figure this out if we consider the web specifically? Yep, exactly. So we could actually probably do some sort of analysis of the links to different web pages to consider their importance. Yeah. So we'll apply this notion of link analysis. And then the question is, which will have more links from other pages? The Wikipedia article for Mount Obama or the Wikipedia article for Barack Obama? And probably you guessed right that it would be Barack Obama, being more well known than the hill that was named after him in 2009. So we could expect that there to be more links to the Wikipedia article for Barack Obama. So this is the concept that we're getting into. We're going to apply what's called a link analysis, and we're going to consider links as votes of confidence in a page. So the more links to a page, the better. So a hyperlink then is like the open web's version of a like in Facebook or in whatever social network you like or don't like. So we consider this as somehow a vote for that page, even if the page is linked in a negative way, even if the page is linking and saying this is a terrible web page. Well, okay, maybe more advanced algorithms could detect that, but links in some sense are considered as a vote of interest in the content of the page. If you link to it, even if you say something negative, you're still interested in the content of the page. So one idea is that we could just count links to a page to determine its importance, use the link count, and we're done, right? Can anyone see a problem with that? And this was very much a problem at around the time Google was proposed as a search engine. So there's a couple of conceptual problems with that. The first is the idea of spam. I used to be a moderator on this question and answer site that's now dead. But a lot of the work was just deleting a bunch of spam because they had really bad spam filters. And this was one of the posts that appeared one day, right? So this is kind of spamming links. There are link farms. There are people who are employed to post comments in different blogs and social media with links back to web pages to help boost ranks. So essentially just counting the number of links is not a great idea because it's not so difficult to create lots of links to a web page. So what we're going to have to consider is somehow the notion of link importance. We're not going to just consider how many links a page has, but how important are those links? Yeah, we're going to take some analysis of the thing that is linking to a document in order to come up with a better ranking solution. So which should count for more, a link from Barack Obama's Wikipedia page or a link from blackmagicspecialist.net. India, I guess. So probably you would guess the Wikipedia page, right? So how do we formalize this into an algorithm? How do we formalize this idea, these intuitions? So this was one of the main differentiators between Google and its competitors at the time. So Google launched on the basis of this idea of PageRank, which was dealing with this problem of how to consider or measure the importance of different web pages. It's quite an elegant solution. There were similar concepts around before, such as hits. So there was some work in this area, but they weren't really being leveraged by websites at the time. So Google, the founders of Google, Andrew Page, Sergey Brin, they came up with this PageRank algorithm. This was very important to the success of Google because it allowed them to have much better results than their competitors at the time. So the central assumption of this PageRank algorithm, page for Andrew Page, but also for web page, the central assumption of this, or sometimes called trust rank, the central assumption of this ranking algorithm is that a page with lots of inlinks from more important pages with few outlinks is more important. Yeah. So a page with lots of inlinks, okay, that's the link count, but not just that. The pages that we're receiving links from should somehow be important to themselves. And those pages should have few outlinks. So if there's an important page that links to 5 different pages, then that's good for those 5 pages. If there is an important page that links to 500 pages, it's less good because it's linking to a lot of things and each page just happens to be one of those. Yeah, is more important. So this is the core idea of PageRank. So this gives us a recursive definition because a page is important if it receives lots of inlinks from important pages with few outlinks. So we're using important twice. So it means that we have some sort of recursion here. Yeah, some recursive definition. We have some cyclic recursive definition in the algorithm. So to define the algorithm, we're going to have to talk about our model. So we're going to take a graph. So maybe you've seen this notation before, maybe in discrete maths, G equals VE. So we have vertices and we have edges. Vertices are nodes. If I say nodes, apologies. Edges are arcs or links. So in the abstract model, we have vertices and edges. On the web, the vertices represent pages, or maybe sometimes websites, and the edges represent links, hyperlinks between those pages or between those websites. So we're going to stick with pages for now. So we're going to take a graph where we have 6 vertices. These are 6 web pages. So this is our set V, set of vertices, A, B, C, D, E, F. And we're going to take some edges between these. These are directed edges. So we're going to represent them with pairs. Yeah, so we have A links to E, A links to F, B links to D, and so forth. So we see the graphical version here, B links to D, and we see its edge represented here as the pair BD. Yeah. So this is what we're going to compute a PageRank on, a directed graph of this form. So which vertex is most important here? Does anyone want to guess? We're going to see what PageRank says about this, but anyone have any sense for which node? Let's see what the chat says. Which?
The one which is more pointing to?
Yep, that would be F, I guess, right? And somebody in chat also guessed F, yeah. Any other guesses? If I told you it's not F? Yeah, okay, so F is a good guess. F is a very good guess, and I'm going to have to justify why it's not F in a little bit. So we're going to have a look at the algorithm. I lost my... Okay, what's going on? Yeah, it's just stalled. Okay, so the most important node is A. I'll explain why a little later. Yeah. F is important. It's the second most important, but not as important as A. So first of all, we have to discuss the PageRank algorithm itself and why it judges A to be the most important. So we're going to need a little bit of notation. So I use out V, where V is a vertex, to denote all of the vertices that are linked to from V. So for example, if we take A, we see that A links to F and A links to E. So the out of A would be F and E. Yeah. In is the other direction. Yeah. So this is the nodes that are linked to, that are linking to that node. So if we take A, for example, then the in of A would be F again and D. Yeah. So D is also linking to A. So these are the in links to a vertex. We are going to define an initial rank, initial page rank, which is 1 over the size of V. So what is the size of V here? It's 6 in this case because we have 6 nodes. So we're going to initialize the rank as 1 over 6. So in general, in PageRank, the sum of the rank will always be 1. And here we have the first part of the calculation. So our initial rank will be 0. And then we're going to go through iteratively updating the rank. So for each iteration, we're going to calculate the rank as follows. For every node, we're going to calculate its rank by summing for all of the nodes that link to it, the rank of that node divided by the number of links it has. So that probably doesn't make a whole lot of sense right now. So we'll take an example to work through the idea. Here we have E links to F, B, and D. Yeah. So what E is going to do at the start, E is going to have a rank of 1 over 6, 1/6, because there are 6 nodes and we're going to divide equally. We assume we take this subgraph of the full graph. We still assume that all the other nodes and edges are there. So 1/6, because there are 6 nodes, 6 vertices in the graph, and we see that E has 3 edges. Yeah. So what E is going to do is split its current rank over the other 3 nodes. So it's going to give F, B, and D, it's going to give each of them 1/3 of 1/6, or a 1/18. Yeah. So it's going to split evenly its rank from the previous iteration with its neighbors in the next iteration. So it has 3 outgoing edges. So it will give 1/3 of 1/6 to F, 1/3 of 1/6 to B, and 1/3 of 1/6 to D. Yeah. So let's take another example. This time we have C, and C again has the initial rank, which is the same, 1 over 6. This time we see that it has 1 edge, 1 outward edge, and that is to B. So how much will it give to B? It'll give everything it has. It'll give 1/6. Yeah, it'll give its full rank to B. Yeah. So this is then summed here. So for B, we summed the contributions that it receives from. Parece que perdimos la conexión acá, perdón. Sorry, a sec. Okay, we should be back. You can see my screen in Zoom. That looks okay. So, see, yep, it should be recording. So sorry for that. The connection dropped. Okay. Yeah, so for B here, we see that B is receiving 1/3 and 1/6 from E, and it's receiving 1/6 from C. So it sums those contributions in order to calculate its rank. And if it has other things linking to it, it will sum those as well. Yeah, so this is the base operation for PageRank. So we could continue doing this process of dividing up the current rank and passing that to the neighbors. So what are we calculating here? A nice way to understand what this algorithm is doing is the random surfer model. Yeah. So we have this idea of someone who is randomly surfing the web, which means that they're on some page. They randomly select a link, a unique link as well. So if we have 10 times the same link to the same page, we count it once. We randomly select some unique link from the page, and we randomly follow that. So we're randomly surfing the web. So then what we're calculating is what is the probability of being at page X after n hops, right? So it means that if we're currently on page E, for example, and the probability of us being here is 1/6, then the probability of us being at step F, B, or D would be 1/3 of 1/6, because we're going to choose between these three. Of course, the surfer can be in the surfer model. We're not going to assume that the surfer is in one place, but we're going to maintain a probability of him being at each of the nodes at all times. So the initial state is that the surfer is equally likely to start at any node, and then we start propagating the probability as we saw in the previous part. Yeah. So if, for example, the surfer is at E with a probability of P, then with 1/3 of P, 1/3 of P, and 1/3 of P, we need to sum here to the probability that they will arrive at F, B, or D from E in the next iteration. Yeah, so we need to sum then all of these things together. So being a probability of being at a particular node after n hops, it's a probability. So if we took the sum of the PageRank of all the nodes, it should sum up to 1. Yeah, so we should get a probability. We know that the surfer must be on some node, right? However, there's a couple of complications, a couple of things that we need to worry about. So what happens, for example, if we have some sort of node here, what we would call a dead node, where we can arrive to G and we have no way out of G. So what would happen with G over time? So it actually depends on how we define the behavior. If the surfer arrives from G and is trapped there, if we assume that the surfer stays in G, then the rank will grow and it will eventually become 1 in this case. Yeah. If we assume that the surfer leaves the graph, arrives to G and just somehow does not continue any further, the process ends, then essentially it will be everything will go towards 0. So we assume the second case here. Yeah. So we assume it goes to 0 because we assume by definition that when the surfer reaches G, that's the end. So they're not at any more nodes in the future. This is just by convention. We actually need to avoid this case. So what we're going to define is that if the surfer reaches a page without links, that the surfer must randomly jump to any page. So actually it says another page, but here it could also jump to itself. It's just easier to calculate. So we assume that if a surfer reaches a node where it cannot continue any further, it will randomly select a page and jump there. Yeah. So that avoids this case, this problem. There is one second case that we need to be careful of, where if we have this sort of case here, it's not really the same case because the surfer can continue navigating, but it will continue to jump between G and I. So what would happen with the G and I over time if we have this sort of case here? So the surfer will, let's say, start here, then move around here, move around here, move here, move here. Eventually, with high probability, it's going to enter into G and I, and then it's just going to jump between G and I for the rest of the time, right? So we'll say that the rank here gets very small, and the rank here gets very high, which is this would be very bad for the web. Yeah? We could easily create this sort of scenario here to boost page rank. So in order to avoid this sort of scenario where the surfer gets trapped in some local web with no way out, some local component of the graph, we're going to define a certain probability that the surfer, instead of following a link, will go to their bookmarks or go to their URLs. So they'll jump randomly to a page. Yeah, so they're going to teleport randomly to some page. So we're going to define a certain probability that essentially on any page, even if it has links, that the surfer will, rather than follow a link, will jump randomly to some page. So this is sufficient to ensure convergence of the algorithm. So in order for this algorithm to behave well, what we need to assume is that we can reach any node from any other node. And we're going to do that by this notion of a weak link, or weakly being able to jump to any other node. So the surfer will jump to a random page at any time with a probability of 1 minus d. This avoids traps and ensures convergence. So this ensures that from any node, we can reach any other node, and we're never going to get trapped in local parts of the graph. So the final version of PageRank is as follows. It's a little bit more intricate now. So we again have our out edges for our vertex, or in edges for our vertex. We have our initial rank, which is 1 over the number of vertices, 1 over 6 in this case. We have as well the notion of vertices that have no outlinks. These are the vertices that if we reach them, we have to jump somewhere else. We have the partition of that, or we have the other vertices, the ones that have some outlinks. In this case, we're going to want to follow a random link with a probability d, which we'll see in a second, or jump randomly with the probability of 1 minus d. So D is the follow a link probability. So D is essentially what are the odds that the surfer will actually follow a link. So what are the odds that if the surfer is at E, that it will follow either F, B, or D randomly? Yeah. So first of all, if we're at E, we throw a dice or something. We take a random number. If the number is less than 0.85, then we choose randomly between these three. If it's the other 0.15 possibility, so if it's less than 0.85, then we'll follow a link. If it's greater than 0.85, then we're going to jump randomly to some other node. That's the idea. So in terms of the PageRank, if we compute these probabilities, when we're computing PageRank, we're computing the probability of arriving to that node from somewhere else. Yeah. So the rank becomes a little bit more complicated, but there are just those three parts that we need to compute. So the first part is the probability of arriving to V from a node, from a link from an edge U. Okay, so that's with the probability of D based on the calculation we saw. We have the probability of arriving at V from a vertex that has no outlinks. So randomly jumping from a vertex that has no outlinks to the current vertex V. And we have the probability of jumping from a vertex with an outlink to randomly to V because of this 1 minus D probability of jumping randomly to a page, even if there's an outlink. So these are the three aspects of PageRank. This is the main aspect. This is the aspect that tells us what's the probability of getting to V from a node that links to V, which would be U. These two aspects are more to deal with some corner cases and to make sure that the graph is strongly connected, that we can reach any node from any other node, even if it's through these weak random links. Any questions or doubts about that? So we will see different, we will see PageRank in the lab. We'll explain it and go through it. So we'll give some more details. So we'll also have a look at how to compute PageRank, and we're going to implement it in lab 8 in order to improve the scores. So in terms of PageRank, the benefits of PageRank, much more robust than a simple link count, because if we have links from pages that have no links to them, it doesn't count the same as, for example, a link from a very well-linked website or web page. There are fewer ties than link counting. This is a major benefit as well, because if we had lots of pages that have 0 or one link, it would be difficult to break the ties in terms of importance. So this gives us a more fine-grained separation or ranking of elements. It's scalable to approximate. Were it not for that, we wouldn't be talking about PageRank. Part of the success of Google is not only does it give some good importance scores, but we can actually approximate it very well. It converges pretty quickly. So we can also distribute the processing of PageRank. We're going to talk a little bit about that in a second. So it's scalable to approximate. Yeah, so we have some ways to run iterations of PageRank, and it will converge, but we can stop maybe after 10 iterations or 15 iterations, or when the ranking doesn't change, or when the difference between 2 iterations drops below a certain value. And convergence is guaranteed so long as from every node we can reach every other node, even if it's through these weak links based on randomly jumping. So Google PageRank was a major part of the success of Google. It helped a lot to improve their search results relative to their competitors. And for that reason, Google became dominant in the market, along with some other factors. Very minimalist interface. A lot of the search engines before Google, they weren't just a search engine. They were like a news page and weather and all this other crap that nobody cared about. So when people started using Google, they would actually wait for the Google page to load, because they thought that was just like, where's all the other stuff? So eventually they learned that you had Google search and also search Stanford for some reason at the start. You had a special option just to search the Stanford web. I promised that I would tell you why A is more important than PageRank. So we see the surfer is a little bit bigger here than let's go back. Actually, I think we should. Seems to be skipping along quickly. So yeah. So why F? First of all, why was F proposed? Because F has 3 inlinks, while A only has 2. For example, E has 1 inlink, D has 2 inlinks, C has 1, and B has 2 inlinks. So why, if A has fewer inlinks, is it more important than F? The key part here for A's success is that F is important, and F's only outlink is A. So if we think about the probability stuff, if we think that it's like... Hola. Parece que la red acá tiene problemas. Vamos a seguir igual. Okay. ¿Pueden ver mi pantalla? ¿Sí? Sí, se ve. Okay, se ve. Okay, so I was explaining why F is or why A is more important than F. F has 3 inlinks, A has 2 inlinks. The key recipe for A's success here is the fact that it has a link from F, and it's the only link from F. So if we consider this probability of being at a certain page after a certain number of jumps, we can see that if we arrive to F, we have no other option but to go to A. So from F, we're gonna get to A. Yeah, so A is somehow equal in that sense with F, right? However, A can also we can also get to A from D, right? So somehow this is adding to the rank of A. So the main thing here is that F, if we arrive to F, we have to arrive to A next. Yeah, so that equalizes F and A. Plus we have this bonus of being able to arrive to A from D. So this is part of the intuition of why this is considered a more important node, because the nodes that are linking to A are more important than the ones linking to F, including F itself is linking to A. Okay. So this is PageRank. Let me skip forward. Yeah. Any questions or doubts about PageRank? No? Okay. So how would we compute PageRank if we wanted to compute this these sorts of graph algorithms at large scale? We have an option, and here we're making a slight deviation back to distributed data processing. Sorry, this should be static data processing, not dynamic data processing. I highlighted the wrong part, sorry. But we have specialized frameworks for dealing with graphs, and they're quite widely used in practice for analyzing graphs for networks. For example, for social networks, that was a major use case. So again, Google were key to proposing this Pragal system. I guess this was maybe they published a white paper in 2010, 2011, if I recall correctly, where essentially they described the system that they had implemented, this abstraction for processing massive graphs on a large number of machines. And this is still a very influential idea called Pragal. So since Pragal was described in this white paper, as we've seen many times before in the course, some big company publishes a white paper, and then these teams come along and they implement open source versions of the concept that was described in the white paper. So the open source versions, the open source implementations, in this case of Pragal, there are various. So there's Apache Giraffe, which I think was implemented by Facebook, if I recall correctly. Or led by Facebook. It's a community tool, open source, but led by Facebook. GraphX and Jelly and Flink. Yeah, so there's a number of GraphX is Spark, a Spark library or module. So there's a number of different frameworks that do something similar. So the core Pragal abstraction for distributed computation or processing of graphs is as follows. It's called a vertex-centric or systolic abstraction. So what it means, what does it mean, a vertex-centric computation? It means that we're going to consider the nodes of the graph to be compute nodes, that they can do something. They can add numbers, they can subtract numbers, they can do stuff. So these nodes are first of all assigned a state. The nodes pass messages, typically along edges, almost always along edges. So nodes can pass messages to their neighbors. And then in terms of receiving the messages, so we see here E is passing D over 1/18. So 1/18 of D, this would be how much rank you would pass through these links in PageRank. And then other nodes are also passing messages to their neighbors, passing how much they're going to share with ranks of the neighbors in the next round. So here we see all of the nodes passing all of the rank share to their neighbors. So nodes can then aggregate messages received and update their state. Yeah, so we see that the initial state here is the rank of 1/6. Now the nodes are sharing their rank amongst each other based on the calculation we saw previously. And each node can then start to, based on the messages received from its incoming neighbors, start to update its state to calculate the PageRank for the next iteration. Yeah. So we can apply this iteratively until some sort of termination criteria is reached. Criteria are reached, or until we decide to stop the process. Yeah. So in this case, we can say, for example, run 10 iterations of PageRank, or we could say run PageRank until the ranking of the nodes doesn't change, or we could say run PageRank until the difference between two iterations is less than a certain value. Yeah, so we compute the some sort of difference between the vectors and stop when the residual is below a certain value. Okay. So this is a vertex-centric computation. This here I'm using PageRank to illustrate this, but you could also consider running lots of different types of graph algorithms in this sort of framework. Yeah, there are certain things still you can't do. This is not sufficient, for example, to distinguish isomorphism of graphs. We can't use this to say if two graphs are the same. Yeah, but there are limits to this, but we can implement many sorts of algorithms for centrality measures. So PageRank is a type of centrality measure that tells us how central a node is in a graph. For community detection, to detect maybe parts of the graph that are isolated, or min cut type operations. There are lots of different types of algorithms we can either implement or approximate using this sort of computation. So in terms of Pragal, this is the core abstraction that you see as someone developing a task on Pragal, that you can send messages to neighbors, receive messages from neighbors, aggregate them, and update a state for the node. So in terms of other features, in brief, we have message passing and aggregation done in parallel. So all the distribution is taken care of for you. Optional message passing to non-neighbors. So if you wanted to message somebody that wasn't a neighbor, you can somehow do that, but it becomes less and less efficient as you start to message from all nodes to all other nodes. You have this n squared problem. Optional global aggregation phase. So we can somehow add this virtual node that is a neighbor of all nodes and send information to it. And from it, we can send information out again. So we could use this, for example, for calculating some of the other probabilities that don't depend on edges in PageRank. We can also change the graph topology. So we can change the graph as we do some calculations, which would be a more rare sort of operation, but it's something we could do that might come with a cost and efficiency still. So in the lab on Wednesday, we're going to use Giraffe to implement PageRank. So you're going to see how to calculate this PageRank measure. We're going to calculate it on the graph of links between articles in Spanish Wikipedia. When you have your ranks computed, you can index. You can use those ranks to boost your Elasticsearch index. So we're going to write some code to use those ranks to create a product of the PageRank with the relevance score. And then you can check your search results and see if they've improved or not. Yeah. Okay, so this is Retrieval. Retrieval again has been implemented as in various open source frameworks. It's been widely used, for example, for analysis of web graphs, social network graphs, transport graphs, wherever we have this sort of graph abstraction. Any questions or doubts? No? Okay, so the last part, I spoke a bit about how Google does its ranking and so forth. It's also very relevant, not just in the context of this course, or in the context of information retrieval, or in the context of wanting to build a search engine yourselves in future over a large number of documents. It's also, there's a whole industry around search engine optimization, or you might have web pages or websites where you might be interested in how could I improve the Google search results for my website, right? So this gets into the area of search engine optimization. So what we saw is still, in some sense, forms the core of Google ranking, but there's a lot of other factors that are taken into consideration in the modern Google search results. So how does Google really rank? Unfortunately, I don't know, because I don't work in Google and Google won't tell me. However, we can make an educated guess based on backwards engineering, and people who are expert in this are called search engine optimization experts, SEO experts. So this survey is a bit out of date. We'll see a more recent one. This is from June 2013, and it's based on a survey of responses by 128 search engine optimization professionals who are hired to help improve the ranks, sometimes by ethical means, maybe some, I don't know, sometimes perhaps by non-ethical means, I'm not sure, to boost the ranking of pages in Google, of pages or websites. So in terms of this survey, we see here domain level link authority features. So this would be like a PageRank variant of PageRank, but at the website level. So uchile.cl or maybe dcc.uchile.cl links to Wikipedia. Yeah, we don't consider the individual pages, we just aggregate into a domain level aspect. So domain level PageRank. Page level link features. This would be PageRank at the level of an individual page. Yeah, so we don't want all pages on a website to be ranked the same. Some are more important than others. So here we have page level keyword and content features. So we have, for example, TF-IDF, topic modeling scores and content using maybe LDA or some other topic modeling algorithms, content quantity relevance, etc. So this is somehow the keyword search scores. Page level keyword agnostic features. So this is how long is the page, how fast does the page take to load, how unique is the page, does it seem to be copied from some other content, does it really look to be distinct from content elsewhere. Domain level brand features. So for example, if your brand, your domain is Uchile, how many times Uchile is mentioned elsewhere as a brand, how often it features elsewhere. Are there press releases about Uchile? Are there other associations with Uchile and so forth? We of course have what one might expect to be very important, the user behavior. So how many users, when they see that result, they click on that result, click-through rate, CTR, how long they spend there, how they interact with the web page. Yeah. Social metrics. This is the idea of how many links are given to this website or this web page on Google Plus, which doesn't exist anymore, Facebook, on Twitter, on whatever social metrics are considered by Google. Then we have domain level keyword usage, exact match keyword domain. So for example, if somebody searches for Uchile or Universidad de Chile, and the domain is Uchile, then we say, okay, well, probably this is relevant somehow for the search. Yeah, if you search for recipes and your domain is recipes.org, that's maybe a helpful sign. Domain level keyword agnostic features. So this is the length of the domain. Is your domain, does it have 4 letters? Does it have 5 letters? Does it have 25 letters? 25 letters would be considered worse. TLD extension, is it a .org, a .com, .shop, this sort of thing. The more established ones should have more prestige. And domain HTTP response time, how long your website takes for a ping, how long it takes to respond to different web pages. So again, this is according to surveys of SEO experts who try to reverse engineer what Google are doing. So they play around with different things and they try to establish somehow what features have the most impact in the Google search results. Yeah. However, at least in this this survey, we see PageRank and TF-IDF kind of covering quite a lot here of the pie of factors. So this is from 2013. I quite like this one because it's quite technical. It actually mentions algorithms, and I haven't really found something so technical. Often it will just say the content of the web page is important, which is not very useful for me. What does that mean, right? How do you measure the relevance or the uniqueness of the content, right? So this is another one from 2019, and not to go through it again, but it's a bit more high level and it doesn't really discuss some of the more technical details. So one interesting thing here is something like mobile friendliness. So now in rankings, if you have a nice mobile page, that helps your ranking quite a bit. If you use this Google AMP accelerated mobile page, they have some framework or something for that helps the ranking. What other stuff is interesting here? Relevance of overall page content. So possibly content's accuracy with respect to accepted facts. So if you seem to be spreading misinformation, it can detect that. So now we have all this machine learning stuff. We have all these large language models and so forth. We can be a bit more advanced in terms of analyzing content for accuracy, for example. We see some of the same stuff here in terms of load page speed. So total amount of on-page content and so forth. So you can use of unique relevant images. Yeah, so if you're reusing images from other websites that appear elsewhere, that doesn't look so good, for example. But if you have high quality images or diagrams that you've created yourself, Google can pick up on this sort of stuff. Yeah, so Google is now looking also a lot at analyzing the content of the web page to see how unique and fresh and interesting and relevant it is compared to what's going on. So as mentioned before, this is how we think Google is doing its ranking. It has published the PageRank algorithm and has published some details, but nowadays it doesn't talk so much about that. Why is it so secretive? Well, because if they publish their algorithms, then people will know better how to exploit their algorithms. So there's always this race between the search engine optimization experts who are trying to artificially boost the ranking of pages that maybe don't have such great content, versus Google, who want to try to prioritize the searches. At least, of course, they have sponsored links and so forth that they're paid to promote, but their algorithm is always trying to search for ways to present users with the documents or the results that they're most likely to be interested in. So there is this sort of race between the people who want to, this tension between the people who want their website to be top, no matter how good or bad their content is, and Google, who want to, aside from commercial results, to boost good content in their results. So for that reason, Google have not published their ranking. So there's also some element here of ranking. What does ranking mean? If we try to define it mathematically, it's not so easy. We're trying to say, okay, we know that Google works very well, that the results it returns are pretty good, but we can't really precisely define what we're trying to go for. We're trying to go for somehow, we're trying to define how important or how likely a result is to be of use or relevant to a particular user. So sometimes in computer science, we have this reluctance to deal with things we can't define precisely. We like our precise algorithms where we have our exact output, where where we need to find, I don't know, the shortest path between two nodes in a graph, and there's a precise, pristine, cleanly defined output. But often in computer science as well, we have these aspects where the output is not so clear, where it's not so clear what we're looking for. And in that case, it can still be very useful to work in this area where we're kind of exploring more somehow, for example, how humans perceive or what humans are interested in, these sorts of aspects. Of course, nowadays, one would assume that a lot of this is just machine learning, that they have a huge amount of machine learning going on in Google, and that they train a lot of their classifiers, so they don't rely so much on particular features, or if they have particular features, that these are all going into some sort of learning to rank machine learning type algorithms. Yeah, so that's ranking. Any questions or doubts? No? Okay. Any questions on Zoom in the chat? No? Okay, so on Wednesday, we'll have the lab where we're going to use Pragal, the implementation of Pragal called Apache Giraffe, which is based on Hadoop. We're going to implement PageRank on Apache Giraffe, compute the PageRank of the graph of Wikipedia links between different Wikipedia articles, and use those to boost the results that we saw, the search results in Elasticsearch. Also, yeah, you all have hopefully your project topics. If not, there's still a possibility with a small discount to propose topics. We'll have to go through them. When I get a moment, I'll go through them and give you some feedback if it sounds good as a project or not. So yeah, hopefully you can do that relatively soon. Okay, no questions, comments? Okay, so I'll stop share. See you in Zoom. See you next Monday or Wednesday. Bye-bye.